Okay, so let's talk about the quantum model of the atom. As I said earlier, today is going to be somewhat confusing. It all comes together tomorrow, and when we're actually doing the electron configuration, it's actually really easy. But I have to give you the background stuff so that we do know how to do it. So today's going to be confusing. Because of that, you have no homework today. Okay, we're just going to let it, yeah, we're going to let you just go home and really think about this. No, no one's going to think about it. Okay, ponder quantum model of the atom and electron configuration. But there is no homework today. Okay, so here we go. So in the TED video, we talked about light behaving as wave and particles. Well, guess what? Electrons also can behave as wave and particles. And a guy by the name of Louis de Broglie, and I know someone in our group, I don't know if it was this class period, got him as a scientist. He was the one to come up and say, he was one of the first ones to say this. So electrons have wave-like properties, but they also have particle-like properties. When we consider that electrons behave as a wave, we see that they are confined to a space that can only have certain frequencies. And, of course, that was our electromagnetic spectrum. That's just another version of it to kind of see about the size of these waves. Okay? And remember, high frequency means what kind of wavelength? If I have a high frequency, then I'm going to have a short wavelength. Okay? Makes sense because the waves have to be short to hit so often in the same amount of time. And that's inversely proportional. Okay? The Heisenberg uncertainty principle states that it is impossible to determine simultaneously both the position, in other words, where it's located, and the velocity or speed of an electron or any other particle. Because if that particle is in motion, as soon as you know where it's at, it's moved, first of all. Or if you're determining the speed, it's always moving. So for saying that it's impossible to know something, he got to put his name on a principle. I have a lot of students that I could put their name on a principle, too. Just kidding. Love you all. Okay. So electrons, of course, are located by their interactions with photons. Okay. And remember we said last week, photons are a discrete amount of particle in the form of energy, light. They have similar energies to each other, which is why we can do the interaction with them. And then the interaction between a photon and an electron knocks the electron off its course. Okay? So Heisenberg uncertainty principle is something you will need to know. A guy by the name of Schrodinger has this famous wave equation, and what he did was he proved mathematically I can never say that word, quantization, I have to say it slow, of an electron energy. And that is the basis of the quantum theory model. Okay? He described mathematically the wave properties of electrons and also the probability of where those electrons are located. So we said last week, we talked about the Bohr model, and it has that planetary orbit type view. Even today, when we draw an atom, we tend to draw that Bohr model look. Okay, it's not the case. They have found that that's not the case. They're not traveling in a specific orbit in one little path, round and round and round and round, like a little roadway around the electron. Okay, that was the older model, the Bohr model. Okay, anybody ever watched Big Bang Theory? They talk about Schrodinger's cat on there before. That's the same Schrodinger. Basically, what Schrodinger did is this is in a nutshell what he did. He put a cat in a box, sealed the box, passed something through, I think a gas or something, I don't even know. And then he said, you can't know if the cat's dead or alive at the same time or something unless you open the box. So you can't know because it's unknown inside. Like, okay.
Did the cat die?
I don't even know. You have to open the box to know. Even though, because the gas, I don't know. Look it up. He's famous for it. Nowadays he'd be arrested on animal cruelty, but back then he's famous for a cat in a box.
I don't get that.
Look it up. It's weird. It's famous. Any kind of physicist, whatever, knows about Schrodinger's cat. Okay? Here is his actual wave equation. The good news is we do not have to do any calculations with that. I have a degree in chemistry, and I never had to do any calculations with that. Okay? But it's just to show you it's a very complicated mathematical equation. Remember in the beginning of the year I told you science is math with a purpose, and that much of the math that we do nowadays was derived or to explain scientific phenomena. Here is an example of math explaining scientific phenomena, and that is the behavior of electrons. So what we know from this is we have, or what we think we know, because remember it's a model, is that electrons exist in regions called orbitals, okay? And an orbital is a three-dimension region around the nucleus that indicates the probable location of an electron. Because why? Why is it probable?
Because you don't know.
Because Heisenberg says you can't know the position and the velocity at the same time. And of course, electrons are moving incredibly fast. So
you could know velocity without knowing position? You just can't know both?
that's what it says, yeah.
Oh, okay.
Yes.
So you can't, because they're so small, you can't predict where they're moving? So it's like,
No, this is a probability. Now, it's a very high probability of where that electron is located, but there could be some outliers, right? The Schrodinger equation is the probability of a single electron being found in along a single axis, okay? So, mind blown, okay? So we think we know where the electrons, and we're mostly sure we know, but we're not 100%, about 90, 95%, okay? So that brings us to describing where these electrons are located, and that we're going to use something called quantum numbers, okay? But basically, the quantum numbers are specifying where that electron is located. You can kind of think of it as the electron's address, if you will, okay? Did anybody go to the Taylor Swift concert this weekend? No. Huh?
Sorry, I only listened. That's on video.
I'm just asking here. There was a concert this weekend. Okay. Anybody go to an Astro game recently? Okay. How'd you know where to sit?
because you want to sit near home base.
No, like how did you know where to sit when you went?
Section says
Yeah. What did you have in your hand that allowed you into the game, and how did you know where to go sit?
ticket
The ticket. And what was on the ticket?
30246.
So it had your section number, right? Had your row number and had your seat number, right? That was your seat for the night. No one else had that seat, right? No one was sitting in the seat with you, right? Okay, so that was your seat. Hold on, I just lost my internet connection. There we go. So that seat or ticket number was your seat for the night. So you can kind of think of quantum numbers as the same way. This is telling you where that electron is located, okay? And no two electrons can have the same seat, okay? They might be in the same orbital, they might be in the same sublevel, same energy level, but they can't have the same seat.
So it's like teeny, tiny latitude and longitude?
Kind of, but not exactly. Kind of, but yeah. Yeah, that's one way to look at it. Never had anybody ask that. That's kind of like that. So there are 4 quantum numbers that we had listed there. We have the principal, the angular momentum, and spin, and I can't remember the third. Magnetic, there you go. So the first one is the principal quantum number. It will always be what's listed first. That is telling us the energy level and the size of the orbital that it's located in. Okay? Telling you energy level and size. We refer to that as N. And so you will see N is equal to, it can be 1, theoretically 1 through a infinity. But right now it's 1 through 7 because we know of the elements that have been discovered or man-made, we have 7 energy levels currently. In theory, we could discover or make a whole bunch of other elements and we could have more than 7 energy levels. But right now, there's only 7. However, in your lifetime, I feel that you will see an 8th one. And that's because,
That's cool.
remember, I think I told most of the classes. So on your periodic table, there's 118 that are on there, right? They've all been named and man-made or discovered. If you look on the periodic table that I gave you, it actually has the names. The one on the wall is old, so it doesn't have them on there. They are, this year, scientists in a couple of different locations started working on man-making or synthesizing element 119. Okay? If they do that, there will be a new, if they're successful in it, and there will be a new period added to the periodic table. You'll have 8 periods now. So then that means your energy level would go up to 8. I feel like y'all will see that in your lifetime. I really do. I feel like I'll probably even see it in my lifetime. Now, seeing a 9th one, they'd have to discover a whole lot more. So, but that is a probability that you could see. Your children probably will, by the time they have chemistry, may have an 8th one on there. Okay, they're man-made. They may not change all the periodic tables in the world just because they are man-made. They don't exist for very long, but it is a possibility. But that's telling you the energy level. the closer you are to the nucleus, the smaller the shape. So let's look at this picture. So here's our nucleus, and we have n is equal to 1, which is your first energy level. N is equal to 2, 3, and 4. Okay? Up to, right now, 7. Okay? The n equal 1 is the smallest, or it's the closest to the nucleus, but it's also the lowest energy level. The further away you are, the higher the energy level. Okay? All right? And so we're going to just go with 4 right now. So we would say, if an electron was in the second energy level, we would say it was in the 2, and then we'd say some other numbers behind it, or some other letters. Okay? But that's your main thing. It does equate to the periodic table's periods. Okay? The next one, and we signify that as lowercase l. I wrote it in cursive so you wouldn't think it was a 1, because a lot of times it looks like a 1. Okay? So it indicates the shape of the orbital. Okay? And the number of orbital shapes is equal to n. Okay? So if there's an n is equal to 1, you can have 2 orbital shapes. If n is equal to 2, you can have 2 orbital shapes. These are your orbitals. They're called S, P, D, and F. And I'm going to show you pictures of them in a moment. Okay? These numbers actually equate to whenever we assign the second quantum number, we're telling us what shape of the orbital. So if we have a 0, we're saying it's an S. If we have a 1, we're saying it's P, 2, D, and 3, F. Okay? That is the order of the filling of the orbitals, S, P, D, and F. Okay? If you need help remembering the order, I have something for you to help you remember. Are you ready? No, it's better than that. Science is pretty darn fun.
Yeah.
There you go. Okay? The S, the only 2 shapes that I ask you to know is that the S is a spherical shape, so it's like a sphere. And then the P has a dumbbell or a figure 8 shape. Okay? So those are the shapes that you do have to know. Yes?
Okay, so it said the number of orbital shapes equals n. So does that mean n that we just talked about, the principal quantum number? Or does it mean...
The principal quantum number. So and if your n is equal to 3, you could have 3 shapes. You would have an S, a P, and a D. Now, if you start getting past 4, it change. I mean, in theory, there are G orbitals and higher, but we don't go there. That's above our pay grade. And there's none that exist in there yet, but in theory, they could exist.
So you could have n equals 3.
And then you would have, so...
L could have a different value, right? Or would L...
Yes. L could have a different value. And I'll hold on to the... So... I don't want to say don't ask questions, but don't get too far ahead because I haven't explained everything, so you're probably really confused right now. And anything I answer at this moment until I explain the next couple of steps is not going to make a lot of sense yet. So maybe jot the question out to the side and see if I don't answer it in a little bit, and then if I don't, because, I mean, there's no way around this lesson. It's just confusing. Okay? I've tried redoing the notes, and it's just there's just no way. I just got to be confusing today, and then tomorrow everything becomes clear. Okay? All right. So the magnetic quantum number is m sub L, and within these orbitals, there's different orientations around the nucleus, or the XYZ axis. And this number is telling you which orientation is it in. Okay? One thing did get left off. I don't know if it's off on yours, but this should say P orbitals have 3 possible orientations. So if S is a sphere, there's only 1 possible orientation around it, right? Okay? But if you've got 3 orientations for the P orbital, there's 3 different slots, if you will, that the electron could go into. And D has 5 and F has 7. And I'm going to show you a picture. Okay? The spin quantum number, this is the easiest of all the quantum numbers, okay? When we have electrons spinning around, there's 2 electrons per sublevel, or per orbital. That's it. But they are both negative, okay? If I were to put 2 negative ends of a magnet together, what happens? They push apart. So we call this, in terms of electrons, we call it electron-electron repulsion. And so they're trying to minimize that repulsion. So they're not like Noah's Ark spinning around 2 by 2 in the orbital. They're actually the 2 orbitals, or the 2 electrons that can be in an orbital, are spinning around in opposite directions. And so we're going to indicate that with a spin up or a spin down. Okay? And the way we do that is when we're showing electrons, we tend to draw them as arrows. And we would show one spinning up, one spinning down. Okay? I draw my arrows like this just so you don't get confused and you're like, what is that? It's just a faster way to draw my arrows.
I thought some of the orbitals could have like 2 and 8.
Again, wait. Okay? I know it's hard to just wait. I'm getting to it. You're getting ahead of me. Okay? All right, now I'm just talking about the spin quantum number, and we assign it a value of half and a negative half, and that's going to indicate which direction is its spin. Okay? So that's how we do that, and that's the fourth quantum number. Okay? So here are the diagrams of the orbitals. We said the S is the spherical one. Okay? So if I am at S, and we're not talking about energy levels because these can exist in different energy levels, but if I am talking about the S, we said the L value is equal to 0. Okay? It's a sphere, so there's only one orientation around that nucleus, right? So our M sub L value could only be 0. Okay? Could only be 0. When we're talking about a p orbital, there are 3 possible orientations around the XYZ axis. Okay? We said for a p that L is equal to 1. We have to indicate which one of those positions or orientations that electron is likely located. So we would do that with an M sub L value, and we just say -1, 0, or 1. This is the third quantum number. Okay? Each one of these little things right here, one electron can fit. It's basically the path. So one can fit over here and one can fit over here. These are called orbitals. Each orbital holds 2 electrons. So this can hold 2 electrons, this can hold 2, 2, 2. Okay? Same thing down here with the D. D has 5 possible orientations. Each orientation can hold 2 electrons. We said L is equal to 2 for the D, right? So we would indicate this by -2, -1, 0, and +1 and 2. So those would be their M sub L values. Yes?
So when you say orientation, do you mean looking at several angles?
Well, are electrons flat objects or are they 3D? They're 3Ds. So in a 3D object, you have an XYZ axis, right? So they're the possible ways that there could be rotating around the nucleus. Okay?
So it's like not by looking at it, like if you're looking at it straight, like parallel to x-axis, parallel to z-axis, and parallel to y-axis. It's looking at it as in like it can travel from like x to z-axis or x to y-axis. You see what I'm saying?
No.
So it's like
I think you're going too deep. Like,
I think the orientation describes like where it is relating to the axis.
yeah, yes.
Okay.
Yeah. So, like, the d orbital has 5 different possibilities around the nucleus, right? And so each one of those 5 possibilities holds 2 electrons. So the d orbital itself can have 10 electrons spinning around the nucleus, and these are their possible ways they could be spinning. Okay? Okay. So here is a summary of the quantum numbers, okay? So, and you're going to see a different diagram that I'm going to have you fill in a minute. So at principal quantum number 1, okay, it only has one sublevel, which is an S, can only hold 2 electrons. Guess what that equates to? Look at the periodic table. What 2 elements does that equate to? Hydrogen and helium, correct, okay? But you can have, so that's the number of sublevels. The number of orbitals is considered to be n squared. So n squared is how many sublevels you can have. And if you're in energy level 2, what's 2 squared? 4. So 4 orbitals right here. 3, which is the P, and 1, which is the S, so it's 4. And then the total number of electrons per energy level is 2n squared. So if I'm at period 4, how many total electrons can I hold? Or if I'm at energy level 4, 32. Because 4 squared is 16 times 2. That's how many electrons it can hold. Now, let's go a little further. Okay, so for electron configuration, there are some rules that govern how we can do this, okay? But I'm going to pause the video so y'all can take time to fill this chart in your notes. Okay, so when you fill this out, remember, this is equivalent to N, so these are where our N values come from. Here we would do our L values, so this would be 0, 1, 2, and 3. That's how we would give those. And then our M sub L is there. And basically, M sub L is equal to the negative L to the positive L, if that makes sense. So if L was equal to 2, you could have negative 2, negative 1, 0, 1, 2. Does that make sense? Sometimes that confuses people when I say it that way. Okay? All right, let's talk about the rules governing how we do electron configuration. There's 3 rules, and they are the Pauli exclusion principle, Hund's rule, and Aufbau principle. Okay? So what the Pauli exclusion principle states is that no 2 electrons in the same atom can have the same set of 4 quantum numbers. In other words, if you go to the Astros game, only you get to sit in that seat. Okay? That's your seat. No one shares it with you. Okay? What that means for us is when we are drawing our electrons, we're going to draw, I showed you we're going to draw an up and a down, which is the equivalent to a half and a negative half. All right? So that's how we would draw that. Because they might be sitting in the same orbital. Let's say this is our p orbital. They might be in the same one, but one's going to be going up, one's going to be going down. Okay? Hund's rule states that orbitals of each energy are occupied by 1 electron before they can get a second one. Okay? We sometimes call this the empty bus seat rule. Empty bus seat rule is a slang for it. So let's say I am sitting on a bus. Only person on the bus is me and the driver. And, let's go with Neelish. And Neelish gets on the bus, and I'm the only person on the bus, and Neelish comes and sits down right beside me. Is that going to be a little creepy? Yes. There's all these other seats he could have sat in, and he sat down right by me. Would I be a little bit creeped out by that? Think that's a little weird. Could have sat somewhere else. But let's say we're all on the bus, and the only seat left is next to me. Then if Neelish gets on the bus and sits by me, is it weird? No, because that's the only seat left. So it's kind of like this. So every orbital has to have 1 electron before they can get a second electron. Okay, so it's kind of referred to as the empty bus seat rule. Like, take the empty bus seats first before you take one and pair up with someone else in a seat. Okay? The other principle is called the Aufbau Principle. And Aufbau is a German word which means to build up. So when we start building a house, do we start with the roof? No. Where do we start? With the foundation. We're going to always put the first electron in the lowest energy level available. Okay? We build from the bottom up, lowest energy to highest energy. Remember earlier I said the further out you get in an energy level, the higher energy level it is. So to put an electron in the 4th energy level is a lot more energy than to put it in the 1st. Okay? So that's the Aufbau principle. There are 3 ways that we can write electron configuration. I'm going to show you 2 today. We're not going to actually do them. I'm just going to explain them. The noble gas one I'm going to save because you really won't understand noble gas until I show you the other one. Okay? So the orbital notation is where we will draw a line to represent one of those orientations. Okay? The lines are labeled with the principal quantum number and the sublevel letter. Okay? We're going to use arrows to represent our electrons. So on a test, the way you'll know is you'll see this word orbital, either orbital diagram or orbital notation, and that means draw the arrows. Okay? So we said a p orbital has p sublevel has how many orbitals? How many orientations around the nucleus?
1.
The p.
3.
3. So we would draw this as this, p. So this is a p orbital. And let's say I wanted to put 4 electrons in that p orbital. So what I would do is I would draw 1, 2, 3 before I would put a 4th one in there.
Are those arrows?
Yes, I draw half arrows. They're faster. You can draw full arrows if you want. I just draw them as half arrows. They're way faster. One year I had someone go like this and draw all their arrows and color them in, and then do this and color them in, and I'm thinking, dang, how long did that take you? It is way too long. Don't do them that way. I mean, if you want to, go for it, but don't complain if your homework takes too long. So that's the way I would do this. What this would equate to is my L would be what? I'm in a p orbital. What would L's be?
2, what?
1. Okay. My M sub L values would be -1, 0, and 1. Is how I would do that. Let's say I was in the second energy level. It would be n equal to 2. So this would be a 2p orbital. Okay? So you could label this under here 2p. Or not 2p.
Just 2p.
That is the question.
Wait, what does 2p?
I'm just making this up. We're in energy level 2. And a p orbital, that's what this would look like. Just go with it.
Doesn't it say number of electrons per sublevel would be 6?
Not per sub. For this, it would say 6, but I don't necessarily have to put 6 in there. What if I only had 4 to put in there?
Oh, okay.
Yeah, you put as many electrons as you have.
Okay, yeah. So then that
So
would be-
tomorrow you will be able to know that if I'm in 2p and I have 4 electrons, this would be my ending electron configuration. So I could go over here and I could say 2p. This is oxygen because it ends in 2p4. That I will show you tomorrow.
Okay.
That I will show you tomorrow. Okay? So remember, the Pauli exclusion says no two electrons can have the same quantum numbers. So that's why when I put the second electron in there, I had to have 1 up, 1 down. Okay? 1 up, 1 down. Never put 2 ups. It's an up and a down. So first thing we're going to remember is we start with the lowest energy level. Second thing is everybody gets 1 before they get a second one. And then when they do get their second one, we're going to go up, 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 and then we're going to go down, down, down. Okay, so our convention is we always give them the up, and then we come back and give them the down. That way everybody's on the same page, everybody's doing it the same way. Because then if you're doing it up when it's supposed to be a down, it's going to change your quantum numbers, and then everybody's confused. Okay? The electron configuration is kind of what I just showed you when I drew that. I said we did that 2p, and we said 1, 2, 3, and we said up, 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 down. Whoop, that is not an up. Okay? And we said that would be a 2p, and then we would say there's 4 electrons in there. Now, you're not going to have just a 2p4. You're going to have the whole thing. I'm just showing you how you get from here to there. Okay? And then noble gas configuration is a shorthand notation that we are not going to look at today. Okay? We'll do that tomorrow. We practice this a lot. And then it'll be like, oh, this is easy. I promise it's easy. But that is where I'm going to end this confusing lesson for the day.